Section 5.4, example 17, using the comparison test. So comparison test, similar to, I believe we went over squeeze theorem. We're looking at two values that end up, like if this one comes out this way, this one comes out this way. If this larger function converges to a value, and then this one's forced to converge to a value as well, just because it's smaller, but it still converges. So what we're going to do is use the comparison test here, and we just pick something that's, so if we want it to converge somewhere, we pick something larger. If we wanted to diverge, we pick something, if we wanted to diverge, we pick something smaller. So let's take a look at these. So starting off with this one here. Okay, so we have 1 over n cubed plus 3n plus 1. So this one here, I know that for all values, so for all values where n starts at 1 and goes off to infinity, I know that this one's going to be smaller than its counterpart. So let's see. So I know that 1 over n cubed plus 3n plus 1. I know this one's smaller than this one here, 1 over n cubed. And the way I know that is we have extra values here. So think of like 1 over 2 is, yeah, 1 over 2, or there we go. 1 over 4 is smaller than 1 over 3. Yeah, there we go. So this is the smaller denominator means it's a larger number. The larger denominator means it's a smaller number. There we go. 1 over 4 is less than 1 over 3. So 1/3 greater than 1/4. Okay, so looking at that, we know that these series are going to be different, but one is going to be a lot easier to compute. So we're going to say that b sub n in this case is going to be the sum as n goes from 1 to infinity of 1 over n cubed. And we have that. And we just learned in the previous section the p series. So based off p series. So based off the p series, 3 is greater than 1. And because it's greater than 1, it converges. So now with the comparison test, since sum as n goes from 1 to infinity of b sub n converges, so does the sum of n going from 1 to infinity of a sub n. And therefore, a sub n converges. Let's bring this down here. Therefore, a sub n converges. All right. Love that one. Now let's work on part B. All right, very similar to the previous one. What I want to prove is I want to find like a smaller value so that way we could prove convergence. And then if not, we'll kind of go from there. All right, so again, larger denominator means smaller number. So 2n plus 1 over 1. This here is always going to be less than 1 over 2n. So what I'm going to propose is let b sub n equal the sum as n goes from 1 to infinity, 2 to the n plus 1, or not 2 to the n plus 1, just 2 to the n. And look at this. So here we have diverging sequence, or not diverging, geometric sequence or series. So geometric series. So since we have a geometric series and 1/2 is indeed less than 1, we have b sub n converging. And because b sub n converges, and because b sub n is always smaller than a sub n, we also have that a sub n also converges. There we go. Ooh, and lastly, we're going to have 1/ln of n. And let's see what happens there. So ln of n. So in theory, it should converge. But I don't think it converges continuously. So if we were to take the limit as n approaches infinity, we would have 1/infinity going to 1. Yeah, I'm not too crazy about that. So what I want to do is find a different value. So let's prove that it diverges instead. So let's look for a value that's smaller. If that value diverges, so does 1/ln of n. So what I'm going to propose, let's just make it a little easy. So why don't we let the other value be 1/n? So here we go with this one, 1/n. So what we're going to prove is let b sub n equal the sum as n goes from 2 to infinity of 1/n. And with this one, we could actually do p series. I think it's going to be easier to prove it with p series. So p series, this is actually 1. So 1 is less than or equal to 1, which proves diverges. So we'll say that b sub n diverges based on the p series, because b sub n diverges a value that's actually smaller than 1/n or 1/ln of n. Because that one diverges, we have to say that a sub n also diverges. And we could have proved this a couple of different ways. I think the book used, what did the book use? The limit comparison. But we used p series. I thought it was easier. And there we go. If you have any questions, please feel free to ask. If not, bye.